Hello everyone. The topic of my presentation today is integrating uncertainty measures in neural networks for improved landmine detection. Landmines and UX detection is a major humanitarian concern in post-conflict regions of the world. The heavily affected countries are Ukraine, Afghanistan, etc. So in these countries, the traditional methods like handheld metal detectors and GPR technologies are being used for technical demining. However, these methods are very slow, unsafe, and expensive, and there is a pressing need for rapid detection of landmines all over the world. So, to solve these problems, drone-based or UAV-based RGB-mounted sensors, which capture aerial imagery of the scene, are being proposed as a silver bullets or the solutions for rapid detection of landmines. However, the landmine dataset, usually superficial dataset, is not publicly available because of several security and privacy concerns. And the recently used models, the neural networks, which are used to classify landmines or detect landmines, are either trained on scarce dataset or they do not handle well for out of distribution data and may not generalize well. So neural networks, when often trained on scarce or limited dataset, cannot first of all generalize on out of distribution data and are easily affected or say more vulnerable to adversarial attacks or perturb input that can easily fool such networks to misclassify the classes. So for critical domains like landmine detection, medical imaging, it is very important to correctly classify the different classes. So in unavailability of a real world data set, I'm using a simulated data set that has 4 classes: landmine, grenade, projectile, and rocket. And this data set is publicly available and the source is mentioned here. And the major idea of my research is to provide uncertainty measure along with the prediction provided by such neural networks. So the basic idea is here to use Monte Carlo dropout technique, which was introduced by Yarin Gal and others in 2015, which says that basically, unlike the standard neural networks which use dropout for regularization, if we use or we enable dropout during testing and we do multiple forward passes or inferences for a single test image, then the prediction can be measured as the average of such number of passes or such prediction, and the uncertainty associated with each prediction or the variance associated with such prediction can be estimated as uncertainty to that prediction. So for my work, I'm basically using a pre-trained ResNet 50 architecture for feature extraction, and I unfreezed the block 3 and block 4, basically layer 3 and layer 4 of ResNet 50, and added a dropout layer with probability of 0.1, and modified the fully connected layer of the ResNet 50 to adjust for my 4 classes. So this data set was previously augmented to create a few more number of data and to adjust for robustness and add complexity to the data for the model. So I trained this network for 100 epochs, and while testing, each image was inferred with 100 forward passes, and the average prediction was calculated from such predictions. So basically the idea here is, so when we enable dropout during testing or during for the inference, each time our network behaves like a different version of the network because of because it randomly drops out some of the neurons. So the model will slightly predict different outputs for slightly for noisy images or where it's not confident well. So the idea here is for the multiple number of passes, the average prediction will give a prediction. However, the variance associated with this prediction we can estimate is the uncertainty of the model itself. So I trained the model for 100 epochs and the training and validation accuracies were above 90%, and the model performed well with the test data set where in the right we can see the class 2 object called the projectile was accurately classified as the second class and uncertainty associated with it was low. However, a noisy image was also though classified or predicted well. However, the uncertainty provided by the model was very high, which indicates that the model is not quite sure about this object. So the basic idea of MC dropout is also that the perturbed images or noisy images will have higher variances. So in case of landmine, it is very important not to misclassify because the technical demining approach for different kinds of landmines, such as say uh, anti-tank mines or anti-personal mines, would be different. And to speed up or reduce false positives, it is very important to correctly classify such landmines. So although the model showed some good results in test images, however, it also produced lower uncertainty with unseen images or uh, out of distribution images. For example, gave the model with the image of a flower, it's obvious that it will associate it with one of the classes. However, the expected result was that uncertainty would be high. However, this was not the observed case and the uncertainty was low. Means that in a real scenario, any random object would also be classified as a landmine, but might not produce a higher uncertainty. So make the network architecture more robust, we have some ideas to say add one of the reasons we thought this happened because was we added a very low probability for dropout. So future idea would be adding more number of layers for the dropout and increasing the probability or some made the training data more complex and hyperparameter tuning to make the network more robust. However, the goal of our this demonstration was to show that we can't blindly trust the aerial drone-based RGB detection techniques without incorporating measures of uncertainties. So with the uncertainty information, we believe that operators can make informed decisions during demining operations, and ultimately enhancing speed, efficiency, and safety, thus by improving the detection reliability. Thank you.